Hi everyone, nice to meet you. My name is Zhang. It's really my honor to present our paper here. This is the title of our paper. It is a Steganalysis method to detect DCT DST-Based HEVC video steganography. This is the outline of my presentation. Firstly, I will introduce the background of our paper. There are two key words of my presentation. The first one is steganography. Steganography is an art and science of covert communication. It conveys secret information without arousing any suspicion and has been widely used by military institutions, government departments, financial institutions, and so on. Steganalysis. It is the countermeasure to steganography. It can detect the presence of secret information in the cover. Thus, it can prevent the leakage of confidential information, reveal illegal information, and is becoming a hot topic in the area of information security. Video steganography often hides secret data in the compression process. According to the hiding location of secret data, the video steganography can be classified into 5 categories. They are inter-prediction mode-based video steganography, inter-block partition type-based video steganography, motion vector-based video steganography, DCT DST-based video steganography, and bit stream-based video steganography. Among them, DCT-DST-based video steganography is a common category, and it is also our Steganalysis focus. For video Steganalysis method, most of them adopt handcrafted classification features. These methods rely solely on the experience of relevant researchers. In recent years, deep learning technology has been widely used in computer vision and other fields. Compared with traditional handcrafted classification features, they can extract multidimensional abstract features by self-learning and do not depend on the experience of experts. This makes CNN-based methods show stronger advantages and motivated us to design a CNN-based Steganalysis method. Furthermore, we analyze the pixel change between cover video and stego video from the perspective of theory and experiments. This figure shows the pixel change rate between cover video and stego video. Each bar represents a video, and the digit here denotes the resolution of the video. The blue bar means the pixel change rate between stego video and cover video is less than 2%. The orange one means the pixel change rate between stego video and cover video is between 2% and 3%, and the green one means the pixel change rate is greater than 3%. We can see that the pixel change rate of nearly 97% is below 2%. That is to say, the pixel change between the cover video and stego video is really tiny. This is the second reason why we want to develop a CNN-based Steganalysis method. Our model consists of 3 parts. The first one is high-pass filter convolution layer. The second one is feature extraction part, and the third one is binary classification part. The aim of the first part is to reduce the impact of image content on the network. The second part is used to improve the representation ability of the CNN and get better classification accuracy. The third part is used to get the final classification results. But this is the whole framework of our model. The yellow one is the first part, that is the high-pass filter convolution layer. The box surrounded by the second black dotted box is our second part, that is the feature extraction part, and the third black dotted box means the third part, that is the binary classification part. I will introduce them one by one. Firstly, the high-pass filter convolution layer. The digit 30 here means 30 convolution kernel are adopted. And the digit 5 times 5 here means that the size of each convolution kernel is 5 times 5. The initial value of each weight is set according to reference 20. Here, 10H is adopted as our activation function. Compared with the common used ReLU function, 10H won't set the negative values of samples as 0, and thus it won't cause information loss and is much more suitable for tiny feature extraction. The aim of this layer is to eliminate the effect of the video content and makes the CNN only focus on the noise caused by the steganography. Now let's see the second part. We can see that this part consists of 5 convolution layers, 3 average pooling layers, and a green block. Here, please note that the green block is the most important part of the second part of feature extraction part. It is the integration of a Steganalysis residue block and SE block. SE is abbreviated for squeeze and excitation. I will introduce them one by one. Firstly, the Steganalysis residue block. This is the structure of Steganalysis residue block. We can see that it adopts the ResNet structure. Because deeper CNN often causes problems such as gradient disappearance, but ResNet can solve the problem. Furthermore, by using ResNet, it can further remove the effect of video content and makes the CNN's output much closer to the secret information. The left figure shows the structure of SE block, and the right figure shows the position of the SE block in the proposed CNN. The blue box represents the Steganalysis residue block, and the green box represents SE block. We can see that the SE block is not independent from Steganalysis residue block. It is integrated to it. This setting is according to reference 21, and the reason why we introduce SE block is that it can model the interdependencies between each channel of convolutional features and thus improve the representation ability of CNN. Furthermore, it only takes slight computational burden. Now let's see the third part of our model, binary classification part. It is a common set, includes a full connection layer and a softmax layer. Now let's look at the experiment part. I will introduce the dataset we used firstly. Here, 110 4 versus 2 versus 0 YUV video sequences are used, which include 22 different kinds of scenes. The resolution of each YUV video sequence is 1920 times 1080. Limited to the computational ability of CNN. Each YUV sequence is separated into non-overlapped subsequences with size of 128 times 128. X265 with version 2.8 is used as the compression software, and HM16.7 is used as a decompression software. The GOP structure we used is IPPP. The quantization parameter is 22. The steganography method we used is reference 19. It is an efficient and classic DCT DST-based steganography. The input of CNN is 128 plus times 128 PGM gray image. That is to say, each YUV picture is required to decode it to PGM format before putting them into the CNN. Furthermore, in order to maximize the difference between samples, not all the YUV subsequences are sent into CNN. The sample selection method is as follows. Since 1920 times 1080 YUV picture can be divided into 128 times 128 blocks. So the first 128 times 128 blocks of the first eye picture are selected, and then the next 128 times 128 blocks of the second eye picture are selected, and the selecting process is repeated until the 128 times 128 blocks are selected. By doing this, 55,000 positive samples and 55,000 negative samples can be obtained. Among them, 49,000 samples are used for training, and the left 6,000 are used for testing. The PyTorch is used as our deep learning platform. Except for rest convolution layer, the weights and offsets of other convolution layers are initialized with k-mean uniform distribution. Cross entropy are used as our loss function. The batch size and the epoch are 32 and 200 respectively. In order to test the efficiency of Steganalysis residue block and SE block, two experiments are carried out. The first one called No SRB SE CNN. It is a CNN without Steganalysis residue block and SE block. Here let's look at this yellow box. It is originally the integration of Steganalysis residue block and SE block. Now it is replaced by a common convolution layer. And the second experiment called SE, no SRB CNN, it adds a SE block directly on the left CNN. We can see from the figure. The number of parameters and the detection accuracy of each CNN is listed in Table 1. We can see that the CNN without Steganalysis residue block and SE block owns the fewest parameters but also the lowest detection accuracy. After adding SE block to the CNN, the detection accuracy can be improved. After further adding the Steganalysis residue block to the CNN, the detection accuracy can be further improved and achieves 91.881%. We also compared our Steganalysis model with other two Steganalysis methods. The first one called SFE-AU. It is the latest work to detect DCT DST-based steganography, and it uses handcrafted classification features. The other one called NRCNN. It is the first CNN-based video steganalysis method, and it is also a universal steganalysis method. Table 2 shows the detection accuracy of the three methods. We can see that compared with CNN-based Steganalysis method, SFEAU owns the lowest detection accuracy, nearly 20% lower than NRCN and the proposed CN. Furthermore, compared with NRCN, the proposed model has higher detection accuracy. Finally, let me conclude our model. Firstly, it is a Steganalysis method to detect DCT DST steganography. The most important part of our model is that it introduces Steganalysis RESD block and SE block. The experimental results show that the proposed model can effectively detect the stego videos with DCT DST-based steganography, and it achieves much higher accuracy compared with the traditional handcrafted classification method and a latest CNN-based Steganalysis method. In future, we will further modify the structure of the proposed CNN and improve its detection accuracy. That's all. Thank you for your listening.